All right, welcome back. So let's go ahead and implement ExtractMax, or remove, whatever you want to call it, to remove the maximum element in our max binary heap. So I'll define our method, ExtractMax, no arguments, and we basically have, going back to our pseudocode, a couple of basic steps. We want to take the first element and remove it and replace it with the last element. So there's a couple orders you could do that in. I think what I'm going to do is first store the value of the max. So I'm going to call it max, just equal to the first value, this dot values 0. So that gives me the first element. Like suppose we had, I don't know, 55. Yeah, sure. Let's just copy this one. If this is what we have, I'm going to take max and set it equal to 55, but it's still in there. Then I'm going to pop the last item off. So I'll call it end this dot values dot pop. So that gives me end. Then I'm going to take end, which is now not there, it's in a variable, and I'm going to put it here. So I just set this dot values 0 equals end. Okay, so that puts 12 here. Wait, was it 12? Yes, that puts 12 right there and removes it from here. And now 55 is in max. So at the end, we do want to return max, but of course, 12 is not at the correct spot. We now need to start that bubbling down process, or whatever, simmering, percolating down, yeah. Okay, so there is one edge case here that we'll come back to. Let me make a note of that so I don't forget. Okay, so once we swap after this point, so this is removing the first element, the max, replacing it with the last element, which is almost definitely not the max. Now we need to do the whole bubble down thing, whatever we want to call it. Trickle down. Okay, so I'm going to define a method to do that. I'm going to call it this dot sink down, just like I did with over here bubble up. I'm going to just make a separate method. Okay, so instead of trickle down, I guess I'm going with sink down. So over here, I'm going to define sink down. Again, no arguments. You could write this to accept actually an index. It's possible that you would want to, something in the middle. You swapped it, or you want it to sink down, or you didn't remove from the beginning. Although that's pretty rare. But I'm just going to make it start at the top element always and sink down from there. The root index of 0. So I'm going to start with an index variable. So index is going to equal, I don't even need anything, it's just going to equal 0. It starts as the very beginning. So if this is what we're working with, and let's say that we just put 33 here, this is what we're working with, it needs to sink down. We're going to start at index of 0, right there, and now we're going to find its children. I'm also going to define a couple other variables here equal to the length of the array, so I'm going to call it length. And just set that to be this dot values dot length. This is just going to help me shorten my code a little bit. And also, I'm going to do one more for the element itself. So I can have the value like this, or I could actually just set that to be 0. So rather than, having to write this to check the element, I'm going to do this dot value 0. So it's just going to be equal to 33 at the beginning. And it's going to stay at 33. We might be moving where 33 is, but the element is always 33. That's where we're trying to position that number, 33. Okay, so I'm going to loop while true, and at some point I'm going to break out, but that's going to be a little ways from now because we have to start with our main logic, which is we found the parent index. Let's find the two children, the left and the right children, 2 times index plus 1, 2 times index plus 2. So let's start by computing left child index, let's do idx, equals 2 times idx plus 1. And then I'll duplicate that line for right child index, but instead add 2. So the first time through, we're talking about 0. Its children are here and here. But if we're talking about 39's children, we're going to multiply that index 1 by 2. So that gives us 2. And then we add 1, index of 3. So its child is here and here. Okay, so this gives us the 2 child indices. I'm also now going to make variables to store the value at those indices. But I can't just right away say, I couldn't do left child equals this dot values left child index. And the reason for that is that there's no guarantee, I could do the same thing for right, there's no guarantee that I'm going to find an element there. There's the potential that this is out of bounds. For example, 41 right here has one child at 12. But if we calculated the index for its right child, it's out of bounds. And so if I tried to access it, I would get an error. So we need to make sure it's valid. And I added this right here. Make sure it's not out of bounds. So I'm going to do that before we actually access the value. I'm going to just, for now, just initialize or declare left and right. But leave them, I'll call them left child and right child, and just leave them empty. Okay, one more variable I'm going to make. And this variable is going to keep track of if we did any swaps in this loop. And at the very end, if there were no swaps, so I'm just going to say if swap is null, we're going to break. So this is our condition at the very end to get out of the loop if we never swapped. So at some point, we're going to set swap equal to true or to something else, but not yet. Okay, now we have those variables out of the way. Let's start with the left side. The first thing I want to do is check, is this index in bounds? So if left child index is in bounds, and that's easy, we could just say if it's less than the length. If it was greater than the length or equal to it, then it's out of bounds. So if it's a valid index, we're then going to set left child, this variable that has no value right now, to equal the value at that index. Okay, so for this case, we start with 33. We calculate left and right child indices. So the left index is the number 1. So we check, is 1 less than the length? That's yes, that is. So we're going to set the variable left child to be this dot values of 1, which is 39. So now we have 39 in a variable. And what we're going to do is compare it to 33, which is our element. And that's easy. We just check if left child is greater than the element, then we're going to set swap equal to left child index. This variable swap is going to keep track of the position that we're going to swap with. So for example, in this situation, 33 is in the incorrect spot. We compare it to 39, and at the beginning, it looks like this is where we're going to swap it to. But then we also compare it to 41, and it turns out, oh wait, 41 is actually the larger number. We're going to swap it with this, with index 2. So we're going to keep track of that index with this variable swap. And we're going to reset it to null every time through, so that if we don't find a number larger, because the only time that we're swapping, we're setting it to anything other than null, is when we find a larger number. If there is no child, left or right, left nor right, I guess, that is larger, then swap will stay null and then we'll break out. Okay, so that's the left side. Now we need to do the right side. Same sort of thing. If right child index, we got to check if it's a valid index before we try and access it. We're going to set right child equal to this dot values right child index. Okay, so that gives us the value like 41. Now we compare 33 and 41. Is the right child greater than element? But there's a little extra logic here because remember, we only want to swap with the value that is largest of the two. So in our case, between these two, the right child is largest. So this would work fine. If right child is greater than the element, it's the last thing. We check the left first and then the right. But imagine that it was the opposite, which, ignoring the fact that this may not be a valid tree, or heap, let's say that this is what we had. If we're trying to compare this to 41, okay, so we decide this is larger, we're going to swap to here. But then we look at the right child. All that we're doing is comparing 33 and 39. Well, this is larger than 33, swap here. But remember, we want to swap with the largest of the two. So I'm going to change this a little bit to say, if we haven't already swapped, meaning if the left child was not larger than element, so that would be if swap is equal to null still, and right child is greater than the element. But there's also another scenario that this doesn't cover, which is when The right child and the left child are both larger than the element, but the right child is largest. So to cover that, because that means that swap is set to the left already. So that would be like in this scenario where 39 is larger than 33. So we set swap to be this index of 1. But 41 is actually the largest, the right child. So I'm going to add a second condition in here where we're going to say, or if swap is actually set to something and at the same time the right child is larger than the left child. And this is kind of a gross little statement here. So we also need parens around this entire thing, or I like parens at least. So I'm going to do it like this and indent so that we can read it a bit better. So these are the two conditions where we end up setting swap equal to right child index, because either the left child never was set, so swap was never set to the left child, none of this was true, so swap is null, but the right child is larger than the element, or swap is not null, meaning that the left side was set to be swapped, but the right child is larger than the left child. Oh boy, it gets tough talking about this stuff sometimes. So if that's the case, we're going to set swap equal to right child index. This whole little conditional here, I shouldn't say little, this long conditional is checking to make sure that the right child is the one we're swapping with, like we have in this case, versus in this case, we're going to swap with the left child. Okay, so at the end of the day, at this point, swap should be set to the left or the right child index or null. And if it's still null at the end, that means we're done. So we have this if swap equals null, break. Otherwise, if this doesn't run, it means that swap is either left or right index. Then we need to actually do the swap. So the swap is going to be this dot values index, which we haven't seen in a while. So remember, it started at 0. So this is the index of the thing we're looking at, 33 to start in our example. Okay, so this dot values index equals this dot values of swap. Now swap is going to be an index. It's either the left child index or the right child index. So it's either this or this. Okay, so that's part of the swap. Then we have to do the other part. This dot values of swap equals element, which we already saved in a variable. So we basically say, all right, the thing that was here is now equal to 41. And now at this index, we're putting 33. So we swap the two. Okay, and the final thing we have to do is update the index. Keep looping and swapping. Oh, this part. The child index you swapped to now becomes the new parent. So here we just set index equals the thing we just swapped to. So that if we started with this and we swapped 41 and 33, now our index that we're starting at is here, and we're looking at the children that correspond to index of 2, rather than 0 where we started. Now index is set to 2, so then we calculate the children, which is going to be 2 times 2 plus 1. So index of 5, 3, 4, 5, and then index of 6, which doesn't exist. So that's why we have this check in here to see if those exist. And we keep going. Okay, let's test this out. See if it works. It's kind of a lot of code. I can move this down or get rid of that. I'll come back to this edge case in just a moment. So we insert, this is what it looks like at the beginning. Let me run the code, see if no typos so far, okay? Now let's try and do a heap.ExtractMax. So we get 55, which is the max. And what does heap.values look like? Okay, so if we look at it, we took 33 and put it here, removed that from the end, and we got rid of 55. And we compared it to its two children. We should have swapped 33 and 41. That's correct. And then we look at 33's children, and there's only one child to compare it to, which is this child, and we don't swap, and so we're done. And that's what we got: 41, 39, 33, 18, 27, and 12. Let's try one more. Let's look at heap.values again. So we took 41 out, and we replaced it with 12 here. And then we repeat the process, which means that we swap 39 and 12. And then we look at 12 and compare it to its children. Well, it has two children, which are 18 and 27, and we swap it with 27, the larger of the two. So 12 ends up back here, 27 ends up right there. And there we go. So this is now what we ended up with, 39, 27, 33, 18, 12. Okay, now the edge case I was talking about. If I keep extracting max, how many are left in there? Okay, here we go. If I try and do it on the last one, it should be empty now. But if we look at it, it still has 12. And I extract it again. I could do it many times, and it still is set to 12. What's happening is just a little bloop up here where if there's only one item left, we are basically popping it off and then reinserting it. Because if this is what our list looks like with the number 12, we're saying, all right, the max is equal to 12. Then the end is also equal to 12. So pop it off and save it in a variable called end. Then we're adding this dot values of 0 equals end. So we're putting it back in there, which we don't want to do. So we only want to do this. We only want to add it back in and sync down if there's anything in there. We should leave it empty otherwise. So let's just add an if and just say if this dot values dot length is equal to, or let's just say is greater than 0. Then we'll run this code. Otherwise, we're not going to because it's empty and we don't want to mess it up. Okay, let's see if it works now. So we have our heap, and I'm going to do a ExtractMax and keep doing that. Okay, and now we hit heap.values and it should be empty. And it is. And every time I try and call it, we get undefined, and that's good. That's how it should work. If I do an insert, we look at heap.values again. We have 10 in there. Let's do one more. Heap.insert 99. It should be in front. Okay, perfect. It's working great. That's the basic way of writing sync down. You can also do this recursively, which I chose not to do here because I feel like it just confuses a lot of students, but you can find some nice recursive solutions. Share some, if you have something that's more succinct, which is not that hard to do. This is pretty verbose, but I wanted to make it sort of step-by-step easy to look at and understand rather than focusing on just making it super brief. Anyway, that is the process to remove the root, whether it is a max or a min. You know, we would have to change a couple things to make it a min binary heap. As far as the comparisons, because we want to look to see if something is greater rather than smaller or the other way around. But other than that, it's the same general approach. So you take the first item, you take it out, you swap it with the last item, and then you sync it down. Okay, I know it's a lot.